Hello. Today we'll be talking about vectors, which should be a good introduction to the course of Calculus 3, or multivariable calculus. To begin, let's talk about what vectors are and what they contain. I'm sure you've heard this before in some other class, particularly Physics 1, but most vectors have a magnitude and direction. Well, in Calculus 3, we're more concerned about the vector's position, or its components that it contains. So, in most cases, we will be graphing our vectors and points and whatnot in the second or the third dimension. So I'm sure you've seen this as well in some other math class, but here we have a regular Cartesian graph in 2 dimensions. We have the x-axis right here, and we have the y-axis right here. In this class, we're also going to be focused on the third dimension as well. So we can graph the third dimension like this, where we have the x-axis right here stretching across this line. We have the y-axis right here stretching across this line. And this will be our z-axis. So notice that I only graphed the first quadrant in 2 dimensions and the first octant in 3 dimensions. And this is only for clarity reasons. So points that exist in 2 dimensions will have 2 components. So we have the x component and the y component. Points that exist in the third dimension have 3 components. We have the x component, the y component, and the z component. Now back to what vectors are. So if we have a vector in the second dimension, it can represent the connection between 2 points. So let's draw 2 points here. Our first point, we can name it A, and our second point, we can name it B. So point A will have an arbitrary value of x initial, y initial, and actually that's just it. So because it has 2 components, we know that point A is in the second dimension. And point B will have x final and y final as the components. Now vectors represent the change between an initial and a final point. So point A will be our initial point, and point B will be our final point, which can also be called a terminal point sometimes. And our vector can be drawn in between these 2 points, like this, using an arrow. Now, naming a vector, we can name a vector a couple of different ways. Most commonly, it's going to be a letter. I'm just going to use V with an arrow on top. In some textbooks, they will use the letter but bold it because the arrow is kind of hard to type out. So our vector V consists of 2 components as well. So we're going to put our vector V here. These components will be encased in brackets, and I'm just going to label them X and Y. So our X and Y components, they represent the change between point A and B. Now let me redraw this so it becomes more clear. But we're going to be talking about how to find these components in a second. So if we have point A right here and point B right here, and a line connecting point A to point B, then would you agree that we would have a couple of components to this vector if we draw some lines like this? So we have a horizontal line, which is the horizontal component of the vector, which is the x component, and the vertical component, which is the y component. So this would be y, this would be x component of the vector. And notice how it makes a right angle. So if point A has x initial and y initial as the components of the point, and B has x final and y final as the components of that point, how can we find the components of the vector? Well, it's pretty simple. All we do is take the final point minus the initial point to get the vector. So we can rewrite the vector as a combination between the points, which is x final minus x initial, and y final minus y initial. Because if we're just looking at the x horizontal line right here, the x final would be located right there, and the x initial would be located right here. And y final would be located right here, and y initial would be located right here. So if you are given 2 points, you can calculate a vector using this equation right here, which is you take the components of each point and subtract final minus initial, and that'll give you the vector. Now this is the same in 3 dimensions. In 3 dimensions, a vector may have an x component, a y component, and a z component. So just down here, x, y, z. And the same, since the vector represents the change between the points, we have x final minus x initial, y final minus y initial, and z final minus z initial. So this is when you're given multiple points. And we can graph vectors either based on the point, or if there's no point, we can just base off the origin. So I'm going to graph vectors that are from the origin onto these planes that I've drawn. So here we have a vector. Let's just name it something different, like u. And this vector is in 2 dimensions, so it should have 2 components. The x component and the y component. And if the vector is in 3 dimensions, then it will have an x component, which is right here, a y component, which is right here, and a z component, which is kind of hard to draw, but it extends vertically down to the plane. And so you can graphically show it like this, or if I draw it next to the plane, I can show the components more clearly. So x, y, and z. And this is a vector v. We can call this vector v as well, where point A exists right here, which is the initial point, and point B is the final point. So here, point A would have 3 components because it's in the 3rd dimension, which would be x initial, y initial, and z initial. And point B will also have 3 components, but this time, since it's the end of the vector, we call it x final, y final, and z final. And we've already derived the equation for the vector down here, but all the components are basically just the final point minus the initial point. Now let's try a few problems where we use this knowledge. So this problem says find a vector where its initial point is located at 0, 2, and the terminal point is located at 5, 6. Since both of these points only have 2 components to them, we know that we're talking about these points and the vector in 2 dimensions. It would really help us if we drew a graph to locate these points. Since both these points are in the first quadrant, I won't draw any more quadrants. So just by estimating where these points are, the first point is located at 0, 2. So about right here. We'll call this point A. And its terminal point is located at 5, 6. So 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5, 6. So approximately right here. We can call it point B. And we want to try to find what this vector is. And the vector points from point A to point B. Remember that the vector has 2 components because it's in 2 dimensions. And the components are represented by the horizontal and vertical lines that are connected to the vector right here. So the vector we're trying to find is vector v. And we have the x component and y component right here. I'm just going to write down the known information to the side. So we have point A and point B. Now we know that the first component is x initial and y initial for the first point. Point B, we have x final and y final. Since we know that the equation for a vector is x final minus x initial and y final minus y initial, we can just plug in all our knowns to solve for the vector. So x final, which is 5, which is part of point B, minus x initial, which is 0, part of point A. We have y final, which is part of point B, minus y initial, which is part of point A. And if we simplify, we get the vector 5, 4. And this vector represents the change between point A and point B. Now let's move on to the second question. If the vector -1, 4, -3 has the terminal point located at 2, 3, 1, find where its initial point is located at. Now, this question gives us the vector and one of the points in 3 components. So we know that this vector has to be in 3 dimensions. So since we know that, we can kind of draw out the vector and the terminal point to see where everything is. Now for these questions, and for most of the questions in Calculus 3, it's always a good idea to graph things out, just to see where everything is according to the plane that you're drawing. So we can't necessarily draw out the vector since we don't know where the initial point is located at, because it's what it's trying to find. But we can draw where the terminal point is, or where the final point is. So we have our x-axis, y-axis, and z-axis written down and labeled. And it says the terminal point is located at 2, 3, 1, which is in the first octet. So 1, 2, and 1, 2, 3 in the y direction, and 1 in the z direction. So our terminal point is located, I want to say, around here. And it's kind of hard to draw in the 3 dimensions, but about somewhere over here. That's our terminal point. Our initial point can be represented by x initial, y initial, and z initial. And these are unknown because we don't know what it is yet. Our vector, which, as you remember, will be the difference between the terminal point and the initial point. So x final minus x initial, y final minus y initial, and z final minus z initial is equal to -1, 4, -3. So since we already know the terminal point, we can plug that in for the final value. So if we plug that in, we find that it's 2 minus x initial, 3 minus y initial, and 1 minus z initial. And this is still equal to -1, 4, and -3. Now we can break this into 3 parts, which is like a system of equations. So we know that 2 minus x initial is equal to -1. We know that 3 minus y initial is equal to 4. And we know that 1 minus z initial is equal to -3. Solving for each of the values, we get x initial equals -1. We have to bring this over to the other side. So x initial will be, negative x initial will be -1 minus 2. Negative y initial will be 4 minus 3. And negative z initial has to equal -3 minus 1. Now we multiply each side by -1 after solving, and we get x initial is equal to 3, y initial equals -1, and z initial is equal to 4. So to verify this, we just plug it into this vector equation right here. 2 minus 3 is -1, so that's correct. 3 minus -1, which is 3 plus 1, is equal to 4, which is correct. And 1 minus 4 is -3, which matches up with the z component. So because of that, we know our initial point is equal to 3, -1, 4. And we can try to graph this. So be right here, 3. And -1 would mean it crosses the other side. And 4, 1, 2, 3, 4. So I'm not going to draw the box, but just approximating it, it's somewhere up here. If we draw the vector, and I will use another color to make this a little clearer. The vector is somewhere over here in the 3D plane, connecting the initial and final points together. And terminal. And I can box the answer just to show that this is correct. Next, we'll take a look at vector magnitude and direction. So the magnitude of vector is the same as the length. If you are given a vector which has two components, an x and a y component, how can you find the magnitude of this vector? Well, first, since it has two components, then it must be in the second dimension, so we can make a graph to look at the vector itself. Now, we don't know the value of x and y, so I'm just going to graph a vector that points out from the origin and represent the x and y with letters. So this is the x-axis, this is the y-axis, and the x and y components of the vector make up a right triangle. If we're trying to find the magnitude, which is represented by the v with the arrow on top and bars around it, how can we find it? Well, it looks like the magnitude of vector is the hypotenuse of this right triangle. And using Pythagorean's theorem, we know that the sum of the squares of the legs of the triangle is equal to the square of the magnitude, or a squared plus b squared equals c squared. So using this knowledge, we have x squared plus y squared equals the magnitude of the vector, or the length of the vector. Now, if we take the square root of everything, we get the vector's magnitude, which we can isolate, is equal to the square root of x squared plus y squared. And this is one of the important equations that we need to remember. The next equation we will talk about is the direction of the vector. So vectors also have direction, and direction is basically the angle between the vector and the x-axis. So this angle right here. We represent this with a theta. Now think back to trigonometry. If we're only given the components of the vector, how can we find out what the angle is? And we can use SOHCAHTOA too. And remember, SOHCAHTOA means sine, opposite, hypotenuse. Sine is equal to opposite over hypotenuse. Cosine is equal to adjacent over hypotenuse. And tangent is equal to opposite over adjacent. If we're only given the legs, we can use tangent to be able to solve for the angle. So tangent of theta, which is the angle we want to find, is equal to opposite over adjacent. And opposite in this case would be the y component of the vector, and adjacent in this case would be the x component of the vector. By solving for theta, we get theta is equal to inverse tangent, or arctangent, y over x. And this is the second important formula we need to remember. Now here's a hypothetical. What if we were given not the components of the vector, but we were given the magnitude and the angle, the direction. How would we find the components then? So if we know the magnitude and we know the angle, we can use the other trig functions to solve. So we can use either sine or cosine depending on what we want to solve for. Let's start with the x component. Now notice that the x component is adjacent to the angle. Since the x component is adjacent to the angle, it is more correct to use cosine to solve this. Remember that cosine theta is equal to adjacent over the hypotenuse. Adjacent would be our x component, and the hypotenuse would be the magnitude of vector v. Now our unknown is the x component, so we want to isolate for that by multiplying both sides by the magnitude. By doing that, we get x is equal to the magnitude of vector v times cosine theta. And this is our third important equation. Now, our other component, which is the y component of the vector, we can solve for because we know that the y component is opposite from the angle. Now, which trig function deals with opposite? Sine does. So sine theta is equal to opposite over the hypotenuse. So the opposite would be our y component, and our hypotenuse, of course, is the magnitude of the vector. So for isolating for our unknown, which is the y component, we get y is equal to the magnitude of the vector times sine theta. And so by using these four equations, we can find out all the properties of the vector in terms of magnitude and direction. So let's use what we learned to answer this question. So find the magnitude of the vector 3, -1, 5. Now this vector is in 3 dimensions, and a vector that is in 3 dimensions has a magnitude which is equal to the x component squared plus the y component squared plus the z component squared. And this is all due just because we have 3 axes in the 3 components, 1 x, 1 y, and 1 z. And we can estimate where this vector is pointing out of the origin because it does not have a position because no points are specified. So we have 3, -1, which is approximately right here, and 5. So our vector is pointing out of the origin like that. So if we dot our lines like this, we can find out that the angle, the right triangle that is made by the vector, is actually between the z component and a combination between the x and y component. Now we know that this length of the component is made by taking the square root of x squared plus y squared, because that is the Pythagorean theorem, just derived. Now taking a look at this triangle, it is the same thing. We can find the magnitude of vector v by taking the square root of x squared plus y squared plus z squared. Now, if you take a square root of a square, if you take a square of a square root, the square root cancels out. So you're left with x squared plus y squared equals z squared. Now, to solve this, it's pretty simple. This is the x component, this is the y component, and this is the z component of the vector. All you do is plug it in to the equation and solve. So x squared, which is 3, plus y squared, which is -1 squared. Now, the square of anything negative is positive, so we can just write 1 squared. Plus z squared. Z component is 5, so 5 squared goes in the formula. Now we start to simplify this. 3 squared is 9, so we write it here, plus 1 squared, which is 1, plus 5 squared, which is 25. 9 plus 1 is 10, so we're left with 10 plus 25 inside the square root. And 10 plus 25 is 35. So the magnitude of the vector v is the square root of 35. Next, take a look at this question. This question is a combination between everything we've learned from position to magnitude and direction as well. If the x and y component of a vector in 3 space is 3 and 4 respectively, and the magnitude of the vector is 6, find the z component of the vector. So 3 space basically just tells us that this vector is in 3 dimensions already. So let's write down everything we know from this problem. So we know what the vector is. So the vector v, it gives us 2 out of 3 components. So it tells us the x and y component is 3 and 4 respectively. So we can put 3 and 4 right here. We want to find the z component of the vector, so that is our unknown. We don't know what the z component is yet. And it tells us that the magnitude of the vector is 6. So the magnitude of the vector is 6. Find the z component of the vector, and it tells us that. So what relevant equations do we need to solve for the magnitude of v? The magnitude of v, which is the magnitude of vector, is the square root of x squared plus y squared plus z squared. So x, y, and z are all components of the vector v. And we are told that this equals 6. We can plug in what we know to this formula here. We know the x and y component, so we have 3 squared plus 4 squared plus z squared equals 6. As this is the x component, this is the y component, and this is the z component. This is an equation with one unknown variable, which is z, so we can isolate z and solve. Taking the square of both sides, we get 3 squared plus 4 squared plus z squared equals 6 squared, and 6 squared is just 36. Now we can just solve the left side and simplify it down so we get rid of all the squares. So 9 plus 16 plus z squared equals 36. Now we can subtract these terms to the left side, so we're left with z squared equals 36 minus 16 minus 9. And the right side, we can simplify it down because 36 minus 16 is 20, and 20 minus 9 is 11. So our z squared is equal to 11, and z is equal to root of 11. So our z component would be the square root of 11, and we can verify this by plugging it back into our vector. So our vector now is 3, 4, and the square root of 11. And if we try to find the magnitude of this vector, we get the square root of 3 squared plus 4 squared plus the square root of 11 squared. So 3 squared is 9, 4 squared is 16, and the square root of 11 squared is just 11 because the square root cancels out when you square it. 9 plus 16 is 25. 25 plus 11 is 36. And the square root of 36 is 6. So since the magnitude of the vector matches with what we calculated, we know that this is the right answer. So the z component is equal to the square root of 11. Now let's talk about unit vectors. Unit vectors are vectors that point in the same direction as the original vector, only that it has a length of 1, specified by the word unit. So if we had a vector, and it doesn't matter which dimension it is in, and we call this vector v, if it has a magnitude of, say, let's say the magnitude of vector v is 4, then the unit vector would point in the same direction, only it has a magnitude of 1. So it's about 1/4 of the vector. We can call this vector u for unit. So our unit vector would have a magnitude of 1. And that would be our unit vector. Now, how do we express this unit vector in vector notation? Well, notice how the unit vector is basically a part of the original vector. So we can calculate what the unit vector is by taking the original vector, vector v, and dividing it by its magnitude. Because dividing it by its magnitude would result in a smaller vector that points in the same direction as the original vector. So this is an important formula that we will use later. Now let's try this out for a problem. It says here that find a unit vector for the vector that has an initial point and a terminal point of 1, 4, -4, and -1, 2, 5 respectively. Please pause the video if you want to try this out for yourself. All right, so the initial point is 1, 4, -4, so initial. And the terminal point is -1, 2, 5. It wants us to find a unit vector, but we don't have a vector yet. All we have is points. Remember from earlier in the video that we talked about how to find a vector from 2 points. It's just each of the components of the terminal point minus each of the components in the initial point. So the vector in 3 dimensions is calculated by x final minus x initial, y final minus y initial, and z final minus z initial. And x final is -1, so -1 minus 1. We have 2 minus 4, and 5 minus -4. So we can just say 5 plus 4. And we know our vector now. By simplifying this, it is -2, -2, and 9. So we can find the unit vector for this vector. Actually, I shouldn't box this yet because we're not done with the question. It wants to find a unit vector for the vector that has an initial point and terminal point of this. So now that we've calculated the vector, we can start by solving for the unit vector. We know the unit vector is calculated by the vector over its magnitude. So we want to find the magnitude of this vector first. The magnitude of the vector is calculated by the square root of the sum of the square of each of its parts. So x squared plus y squared plus z squared. And by plugging in each of the points into the formula, we get x squared, which is -2 squared. I can just write 2 squared because the negative cancels out when you square it. Plus y squared, which is 2 squared again. And plus z squared, which is 9 squared. To simplify this, we have 4 plus 4 plus 81, which is 8 plus 81, which is the square root of 89. Now, since we have our magnitude and we have our vector, we can plug it into the formula of the unit vector and find what it is. So our unit vector will equal each of the vector's components divided by the magnitude. So we'd have -2 over the square root of 89. We have -2 over the square root of 89. And we have 9 over the square root of 89. An alternative way to write this is to factor out all the 1 over square root of 89 and write it to the side of the unit vector. And this is usually good to do to simplify the look of the vector at the end. So -2, -2, and 9. By multiplying the vector by 1 over its magnitude, we get a vector which length is 1, and it points in the same direction as vector v. So this would be our unit vector, which answers the question. Now let's talk about vector addition. There are a couple ways to do vector addition, one of which is algebraically and one of which is geometrically. The algebraic method is a bit easier, so we'll start with that. Let's say we have two vectors, vector v, which has components x1, y1, and z1. And we have vector w. Vector w would be x2, y2, and z2. To add these two vectors together, it's as simple as just adding each of the components together. So we have x1 plus x2, y1 plus y2, and z1 plus z2. And that's it. So if you want to add vectors together, just add each of the components together. But what does this look like graphically? So let's say we have vector v that points in a direction like this. And let's say vector w points in a direction like this. How would this look like if we added these two vectors together? Well, there are two methods to add these together. The first method is head to tail. So you can add a vector head to tail by just putting its head to another vector's tail together, and then connecting the head to tail at the end. So let me show you what I mean. So this is vector v, and now I'm going to connect it to the head of vector w from the tail of vector v. It kind of looks like this. So this is vector v, and this is vector w. Now I've connected the head of vector v to the tail of vector w. Now what? Now I will connect the head of vector v to the tail of vector w, and this will give me a resultant vector that is the sum of v and w. So we'll connect the head of vector v to the tail of vector w, like this. And this vector is v plus w. Now the second method to add this geometrically is called the parallelogram method. And this method is also very simple. So let's assume these vectors are in 2D plane, so in 2 dimensions. And just draw the axis higher. Now we'll move all of these vectors to the origin, as because these vectors do not have position, they do not have points to go off of, which means we can move them around the plane and they'll be the same no matter what. So let's move these vectors to the origin. Vector v would look something like this, and vector w would look something like this. and we can label them as such. Now, we'll make a parallelogram out of these vectors. We're going to move vector v and make a copy of it over here. And now we're going to move vector w and make a copy of it from vector v. By doing this, we essentially make a parallelogram. And this parallelogram will give us the resultant vector if we connect one corner to the next of it. So let me just erase most of this so I can continue. So by connecting the vector from its origin to where the parallelogram coincides, right here, that will give me the sum of v and w. Let's try this on an example. So solve u plus v when u is equal to 3, 4, and v equals -1, 2, using the algebraic method and the geometric method. So algebraic method is pretty easy. So we have two vectors. We have vector u, which is 3, 4, and we have vector v, which is -1, 2. Now u plus v is as simple as adding these components together. So 3 plus -1 would be the x component, and 4 plus 2 would be the y component. And by simplifying this, we get 2, 6. Now the vector 2, 6 would look like a horizontal translation of 2 units and up 6 units from the origin. Something like that. We can verify this by graphing it. So now that we've solved this algebraically, we can solve it geometrically as well. By graphing, these vectors have 2 components each, so we know that it is in the second dimension. The first vector, 3, 4, which is 1, 2, 3, and 1, 2, 3, 4. So vector u would point up like this. Vector v is -1 and 2, so we need to extend this axis. And just to make sure, this is a y, this is x-axis, and -1, 2. To label them, this is u, this is v. Okay, so because these vectors are from the origin already, we can use the parallelogram method, or we can use the head-to-tail method to add these vectors. The parallelogram method would be easier in this case, just because the vectors are already pointing out of the origin. So we can just draw lines connecting these vectors together. So this dotted line represents the translation of vector u over to vector v. And the vector v can be drawn over here, which represents the connection between vector u and vector v. So in this case, this is kind of like head-to-tail addition, but we're doing this twice so that we can get a point right here to connect this vector to. Now the resultant vector, which is the sum of the 2 vectors combined, would stretch from the origin up to this point. And the value of this would be 2, 6. So this would be u plus v. And this would be 2 units and then like 6 units up. And the final topic today is scalar multiplication, parallel vectors, and IJK notation. So what is a scalar and how does it differ differ from a vector? Well, a scalar is just a constant. It's like a number, and it scales things. So if you multiply a vector by a constant, what will happen? So this constant I'll represent with a c. If we have a vector in 2 dimensions, so we have 2 components, what happens if we multiply by a constant? Well, by multiplying by a constant, we need to distribute it to each of the components. So remember, when we did unit vectors, we can factor out a scalar. Well, in this case, we can distribute in a scalar, so the vector would look like this. So c times x and c times y. Now, this vector is basically the same as the normal vector, xy, only that both components are multiplied by a scalar, which means that these vectors are parallel. So vectors are parallel if they're scalar multiples of each other, which means that a unit vector and the normal vector are parallel because the unit vector is a scalar multiple of the original vector. So let's say this vector right here is vector v, and this longer vector right here is vector w. Vector w is a scalar multiple of vector v because vector v and w are parallel to each other. So you can write vector w as a scalar multiple of vector v, or vector v as a scalar multiple of vector w. Let's do c prime. Like that. Now, if the scalar is bigger than 1, so if the scalar is bigger than 1, then the resultant vector will be longer than the original vector. If the scalar c is less than 1, but greater than 0, the result is shorter than the original vector. Now, if the scalar is 0, well, this would result in the 0 vector. And the 0 vector happens when all the components of the vector are 0. So the vector would be 0, 0, or 0, 0, 0, depending on how many dimensions you have. If c is negative, so c is less than 0, but c is greater than -1, then the result is the vector in the opposite direction. If c is less than 1, less than -1, then the vector would be in the opposite direction but longer. Which brings us to an interesting property of vectors. So if you multiply a vector by -1, you are flipping the vector in the opposite direction. So let's say we have a vector that looks like this. Call it something different this time. Maybe vector A. This is just to show that you can name vectors by any letter of the alphabet. Now, if we multiply A by -1, what happens to the vector? Well, the vector gets flipped. So this new vector will be in the opposite direction, but it will have the same length as A. So the magnitude will still be the same. And this is -A. So these magnitudes are still the same. It's just that the negative version of the vector is pointing in the opposite direction. Let's try a few problems with this property in mind. So if the vector v equals I plus 2j minus 3k, find two vectors parallel to the vector v that have a magnitude of 5. One thing that we can do is write vectors in ijk notation. And IJK notation is really helpful when you want to clarify that the vector starts from the origin. You can do this by using the basis vectors I, j, and k. Now, the basis I, j, and k vectors represent unit vectors pointing out from the origin. So this would be the vector, actually, this would be the vector I. This would be the vector j. And this would be the vector k. Because these are basis vectors, all of these have a length of 1, where I is 1, 0, 0, j is 0, 1, 0, and k is 0, 0, 1. If we put them in the context of vector v, we notice that it is multiplied by coefficients before the I, j, and k. And these coefficients are noted, are scalar multiplied by these basis vectors. So according to the question, the x component is 1 times the basis vector I. And that's just 1, 0, 0. The y component is 2 times the basis vector j. So we get 0, 2, 0. And finally, the basis vector k is multiplied by the coefficient -3. And remember, the negative still counts, so don't leave it behind. And so -3 times k is just 0, 0, -3. Now, adding all of these vectors together will give you the vector v in vector notation form. So if we just do that really quick, 1, 0, 0, plus 0, 2, 0, plus 0, 0, -3. Now we can add each of the components together to get 1, 2, -3. So by using IJK form, we can express the vector as a sum of the basis vectors combined, given that each of the basis vectors is multiplied by a specific coefficient. So this vector, according on the 3 space graph, will look something like this. So I would remain unchanged because it's multiplied by 1. J would be elongated to 2 times its length. Actually, I just realized that I wrote this wrong. K is actually the z component, so it should be pointing upwards. So this should be k, and this should be j. So j points in the y direction, k points in the z direction. So 1, 2, -3. The j vector is elongated twice its length, so about right here. And the z component is multiplied by -3. Now, any vector that's multiplied by -3, or any vector that's multiplied by negative, is flipped. So 2, 3. The results would be somewhere below the xy plane, so somewhere down here. So we draw like a box representing this. Then we can find out where exactly the vector points to. So the vector points somewhere down here. And let me just use a new color. Points somewhere down here. And that is our vector v, which has component of 1, 2, and negative 3. Now, back to the question. So if the vector 1, 2, negative 3 exists, find two vectors parallel to the vector v that have a magnitude of 5. Now, since we are dealing with magnitude, we can first write down the formula for the magnitude of vector in 3 space. So the magnitude of vector in 3 space is the x component squared plus y component squared plus the z component squared. Let's try to find the magnitude of this vector currently by plugging in each of the components. So 1 squared plus 2 squared plus 3 squared. And the square root of all of that combined equals 1 plus 4 plus 9 equals 1 plus 4 is 5. 5 plus 9 is 14. So that'd be the square root of 14. So the square root, the magnitude of this vector is currently the square root of 14. And we want to get this to where the vectors have a magnitude of 5. Remember that vectors that are parallel to vector v are scalar multiples of it. So if we can, for example, find the unit vector, remember that the unit vector is just the vector v over the magnitude of it. That is equal to 1 over the square root of 14 multiplied to the vector 1, 2, negative 3. So this would be our original vector, and since we're multiplying it by a scalar of 1 over the square root of square root of 14, then the unit vector is parallel to the original vector, vector v. Now, how do we get this to where the vector v has a magnitude of 5? We know that the unit vector currently has a magnitude of 1. So let's just label this. The magnitude of the unit vector, u, is 1. So to get this vector to have a magnitude of 5, all we need to do is to multiply the unit vector by 5. So multiplying the unit vector by 5 gets us 5 over the square root of 14 times 1, 2, negative 3. And this is great. We found one of the vectors that is parallel to vector v that has a magnitude of 5. What are we missing? So we want to find two vectors that are parallel to vector v that have a magnitude of 5. We can also multiply this by negative 5 to get another vector, because vectors that are pointing in the opposite direction can also have a magnitude of 5 and are also parallel to the vector v since it's a scalar multiple. So by putting the plus or minus sign, we're saying that the vector 5 over the square root of 14 times the vector 1, 2, negative 3 is parallel to the vector 1, 2, negative 3. Notice that the answer and the original vector have the same vector, only one is multiplied by a scalar, and that is what makes it parallel to the vector v.